Okay, this is the Lewis structures packet. It says how many valence electrons does the carbon atom have before it bonds? And so what we do is we look at the periodic table and we would find that carbon is in the fourth row or fourth column, and so it has 4 valence electrons. And the chlorine atom is in the halogen, which is the 7th row. And then it says, since it's made up of 1 carbon and 4 chlorine, how many total does it have? Well, we'd have the 1 times the 4 valence electrons plus 4 times 7 valence electrons. And that's 28, and 4 is 32 valence electrons. And the next thing says verify that there are 32 pictures, 32 electrons, and we could count. Pretty easy to count these. That's 8, another 8, another 8, and another 8, and 8 times 4 is 32. So we are in good shape there. Put a check mark there. Find the sum of the valence electrons for NF3. Well, we have 1 N, and that is 5 valence electrons, plus 3 Fs, and that's 7 valence electrons. And that would be a total of 26 valence electrons. And if I scroll back up to the top here, I'm going to count them up. So I've got, let's do a different color here. We'll do 8 there. We've got 8 here, and we've got 8 here, and we got another 2. That is a total of 26 valence electrons. Okay, so what is meant by the central atom? It's the one in the middle. One, all the other atoms bond to. Sulfur is the central atom, SF3. You can tell which atom is the central atom by simply looking at the formula. It's usually the one there's the least of. That's kind of in this thing. So in this one, carbon is the least, phosphorus is the least, and silicon is the least. And that is the central atom in every single one of those. It doesn't always work out that way, but for our purposes, it does. How many electrons are in here? Well, we've got 1 times P, which is 5 valence electrons, plus 3 times 1 valence electrons. We got a total of 8 valence electrons. Si is 4, plus 2 times 6 is 12, 16 valence electrons. And then it says CO3 is 22, but we got CO3 minus 2 as 24 instead of 2. Those 2 electrons came from probably a metal, right? They must have come from somewhere else, so probably a metal that wanted to lose 2 electrons, or 2 metals of losing 1, right? NH4 plus is 8, so the NH4 gave up 1 electron to a nonmetal, somebody that wanted to get it. So in this, for a negative charge, we need to add an electron, and for a positive charge, we've got to subtract an electron. And then the last one, number 14, for each of these polyatomics, determine the number of valence electrons. Well, we got 5 plus 6 times 3 plus 1 is 6 plus 24. S is 6 plus 4 times 7 is 34. H3O plus, we know is H is 1 times 3 plus 6 minus 1. That's 5, that's 8. PO4 is 5 plus 6 times 4. 24, 29 plus an extra 3 is 32. Okay, and the next page has a bunch of different structures, and now it asks you to draw some. So you've got to use those rules to draw some structures. So let's see if we can't figure this out together here. I got NO3 minus 1, and we got to draw it with single bonds first. So let's do this. We're going to do N single bond O, single bond O, single bond O. Oh, we should have probably figured this out. This 5 plus 3 times 6 plus an extra 1 right there is 18, 19, 24. 24 valence electrons. I'm going to forget that number for right now, and I'm just going to fill in all the ones we need. We need 1, 2, 3, 4, 5, 6, 7, 8. This guy needs another 6. This guy needs another 6. And this guy needs another 6. And now we can go ahead and count all of them. We got 2. Let's just count them with a different color here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So in order to draw this structure, this would have 26 valence electrons, which would mean that it must have gotten an extra 2 electrons from somewhere else. So that one doesn't work to make NO3 minus 1. Oh, I'm sorry, it doesn't mean negative 3. Okay, and the next one is, and then so we're going to try drawing it again here, and we've got N, let's try a double bond. And then this N doesn't need any more electrons. This O only needs 4 more. And let's go ahead and count them up if we see if we got any. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And that matches the 24 there. So this has a charge of 0 and is the way that NO3 looks. And the next question has us draw SO2, which is 6 plus 2 times 6. It's 18 valence electrons. S is our central atom. Let's try it to a single bond. We would need a 4 and then 6 on the outside. And we said this was 18 valence electrons. Oh yeah, right there. And we're going to go count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So in order for this to work, we would need it to be a negative 2 charge. So let's try with a double bond. Fill in our dots. And let's count them up. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Matches our 18. So this is SO2. Okay, so here's some practice with this. NO3 minus 1 is going to be, we just count it up and we try it with single bonds first. So we've got N, single bond O, single bond O, single bond O. And we've got 5 plus 6 times 3 is 18, plus another 6 is 24 valence electrons, and this structure has 26, so that's not going to work. So if I try it with one double bond first, now this structure has 24 valence electrons, so this is what N3 minus 1 looks like. CH4 is 8 valence electrons. I've got a C, I've got an H, and I'm done because hydrogens, these guys, only need to follow the duet rule. So if I look at that, each hydrogen has 2, this carbon has 8, we're in good shape. NF3, N is 5, plus 21 is 26 valence electrons. It has 26, so we're in good shape there. SiO3 minus 2 is 4, plus an extra 2 right there, plus 6 times 3 is 18, so we got a total of 24 valence electrons. And I already know what this guy's going to look like. It's going to look just like the one that has 24 valence electrons and has 4 in it, which is right over here, NO3 minus 1. So I'm going to put a double bond on one of these oxygens. And so if I do that, I end up with 24 valence electrons, and I'm in good shape. HCN, they told us that C is our middle. If I try with just single bonds, I end up with 2, 4, 6, 8, 10, 12, 14. And how many did I start with? Ooh, I forgot to figure that out. H is 1 plus 4 plus 5. We got 10 valence electrons to work with down here. And I just said that there were 2, 4, 6, 8, 10, 12, 14. Okay, you know what that means? I need 2 fewer electrons. So I'm sorry, 2 more bonds. And if I count those up, they should add up to that 10 valence electrons. 2, 4, 6, 8, 10. Done. H2O, we talked about this one before. NH4 plus, got 8 valence electrons to go with. And CCl4 is 4 plus 28 is 32. And put in all the dots, that's 8, 16, 24, 32. H2O, we already said, was drawn like that. SO2 is 6 plus 2 times 6 is 18. So S, single bond's not going to work. Oh, too many. All right, so we got 2, 4, 6, 8, 10, 12, 14, 16, 18. That matches. Okay, single bond is shared pair of electrons, 2 shared pairs of electrons, and 3 shared pairs of electrons. And in terms of which one's the strongest, it's going to be harder to break the triple bond. It's just like Tiemann and I, like we're attracted to each other in 3 ways. I'll leave it to your imagination what those 3 are. Okay, so it says in your answer to question 3 consistent. Yeah, it is. It is because that one had the most amount of energy to break it. So the relationship between bond order and single to order triple, they're the same, right? These are the same thing. But bond length and bond energy are inverse. So as there's more, as this gets shorter, it takes more energy to break them. Which bonds are the shortest? The triple bonds, which you would expect. Like the more bonds you have with something, the closer you are. And the structure for benzene, the bond order for the CC bond it's single, right? So this is just talking about the CC bond. We would expect it to be 1. And the carbon-carbon bonds, well, here's the deal. We would expect this to be a single, a double, a single, a double, a single, a double. And so that would match the one from the previous page. But here's what it's going to explain in the next part, which is that these aren't really, and this is kind of a hard one to read, so I'll kind of flip through it with you. These aren't really double or single bonds. The idea is that up here, these electrons are spinning. Remember, we talked about like electrons in an atom as being like force fields, that they're moving so fast that they occupy the entire sphere all at once. Well, same thing here is that those electrons are really in all those spots. So what we found when we actually looked at empirical data was that in order to break this bond or this bond, it took the same amount of energy. So we don't really have a double bond here or a single bond there. We have what we call a 1.5 bond. It's halfway. And what we found was instead of it being 150 or 130, you might have guessed this already, that it really was 140. Okay, so the nitrate ion is represented by these resonance structures. Draw the 3 resonance, the 3 structures below. The only difference will be the position of the double bond. So really, it could be this. It could be this. Or it could be this. Right? And I could fill in all the dots. And again, we'd have to put in a -1. And then we'd have to put in a -1 there. And what we're saying is that these are resonating with one another, that they are close to one another. Okay, so we put a -1 there. And then the next question, why were there three structures instead of 2? Because the double bond could be in 1 at 3 spots. Which would mean that the bond order here is what we call a 1 1/3. Because realistically, the bond is being shared equally here, here, and here. And that's what the next question asked you. So this is bond order. The bond length would be somewhere, we'd add an extra third, and the bond energy, we'd add an extra third. So it all goes back to that 1 1/3. CO3 minus 2. All right, so carbonate, CO3 minus 2, we've got 4 plus 3 times 6 plus an extra 2 is 24 valence electrons. And because it says 4, I know that one of these is a double bond. You might have needed a little bit more time to figure that out. That's a -2, but that double bond could be in 1 of 3 spots because it really isn't a double bond. It's really in all of those places at once, but not exerting a double bond. The last one is going to be C, double bond O. Concerning the structure you drew in question 1, what is the bond order? 1 1/3. CO2 could be this, or it could be this, or it could be this. Okay, and the next question says, comparing the structures you drew for questions 1 and 3. So let's go back and take a look at those. 1 and 3. Which one have the longest bonds? Well, the bond order here is 2, and the bond order here is 1 1/3. So the longer bonds would be on the fewer bond or the less bonds, right? So it would be the strongest bonds would be the longest bonds would be in the 1 1/3. So question 1 are the longest bonds. The strongest ones would be the bond order of 2. Okay. And then it says, in general, the stronger the bonds, the shorter the bonds. And then in general, double bonds are longer than triple bonds. And bonds with low bond energy are weaker than bonds with high bond energy. Okay, and then it says number 1 says examine the structure for the cyanide ion Cn-1 below. Label the formal charge for each of these atoms. So this carbon's brought to the party 4 electrons, according to the periodic table, and it would leave with 5. So this is a -1. And this N brought 5 electrons and is leaving with 5. So that has a formal charge of 0. And overall, the charge of this, it said, was -1. Here's the 2 structures for CHNH2O. Are both of the structures legitimate structures, i.e. do all atoms have 8 electrons? Well, let's examine. So we've got, well, not all of them need 8 electrons. This hydrogen only needs 2, right? And this hydrogen only needs 2, and that hydrogen only needs 2. But this carbon has 2, 4, 6, 8, and the oxygen has 2, 4, 6, 8. So we're in good shape there. 1 for hydrogen, 1 for hydrogen, 1 for hydrogen. The nitrogen is 2, 4, 6, 8. Carbon is 2, 4, 6, 8. And the oxygen is 2, 4, 6, 8. So yes, they are. All right, formal charges. Let's take a look. So again, how many did you bring in the party? So this each of the hydrogens 0, and they're always going to be 0 for the most part, because you'd have to force electrons on there. Carbon brought 4, leaves with 4, so that's 0. And this oxygen brought 6 and is leaving with 7, so that's a -1. And the nitrogen brought 5 and is leaving with 4, so that's a +1. Overall, the charge is 0. This carbon started with 4, ended with 4. Oxygen brought 6, leaving with 6. Nitrogen brought 5, leaving with 5, 0. So which structure is the best structure? The second one. Less rearrangement. And then it says draw the structure for ClO3 minus 1. So Cl has to be the middle. We got O, 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 and it's going to be a minus 1. So let's see if this works. I'm going to put in my electrons. So I need 6 on each of the oxygens. And 2 on there. And we started with 7 plus 18 plus another 1. So that's 26 electrons. And I believe there are 26 electrons in this. So let's just take a look. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And the formal charge on each one? All right, so let's take a look here. Let's use black. So oxygen came with 6, is leaving now with 7. So that's a minus 1 there. Chlorine came with 7 and is leaving with 2, 3, 4, 5. So that's a plus 2. Minus 1 on each of the oxygens. 3 negative 1s and a positive 2 is a negative 1. We're in good shape.